All right, so group 9, what'd you get?
We got t squared equals 4 pi squared r cubed over g times big M.
And that's right. And I think I was walking around the room and looking at this. You guys, excuse me. You guys all agree with this? Okay. Now, you just did what Kepler spent 17 years trying to do. But we made a simplifying assumption that it was a circle. You had Newton's law of gravity, which Kepler did not have. You also had that force of gravity is a centripetal force. There was no understanding of centripetal force. There was no mathematical model for it in the time of Kepler. Kepler knew this, I'm sure, but so you had some mathematical tools that make it fairly straightforward. He had just the position of Mars in the night sky to go on. And at one point he made an arithmetic mistake and it set him back like 3 years. So imagine working on a physics problem for as long as you've been alive and getting stuck and getting nowhere and then having to move because you're trying to keep the authorities from burning your mother as a witch. I mean, he had a tough life. But when he finally figured this out, actually what he did is he figured this out. He was ecstatic. And he also knew that hundreds of years in the future, some goofy high school physics teacher would be talking about him because he knew he made a discovery of historical significance. And so good for him. Now, he didn't have this, because he didn't know what the gravitational constant was. He had no concept of what the mass of the sun was. But he set it up in ratios. If you have two planets, like let's say the sun, there's Mr. Sun, right here. And then you have a planet here. And then we have a planet out here, further out. This has a period. We'll call this the period 1. That's the time to go around once. This planet has its own period. This planet has its radius. This planet has its radius. And what he did is he set it up as a ratio. And then he said period 2 squared over period 1 squared is equal to, he's messing this up. Hold on a second. Is equal to r cubed, or I'm sorry, r2 cubed over r1 cubed. This is how you set it up with ratios. Why would you set it up with ratios? Because, t squared, we said t squared equals 4 pi squared over gm over r cubed. So let's do that. Oh, this has a 4 pi gm. Well, 4 pi squared, that's a constant. G is a universal gravitational constant, and there's m. It's the mass of the sun. This other planet also has 4 pi squared over gm, and they cancel out. See, everything cancels out. Everything that's the same cancels out when you set it up as a ratio. Okay. So this is how he expressed it, and Newton used these results as well. Now, Kepler did not know why this was true. He just showed that these mathematical patterns matched the data. And it was, and so that was based purely on observation and some calculations to go around that. And then Newton came along later and explained why it was true. Oh, because the force of gravity matches this mathematical pattern. It's moving in a circle. and you blah, 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 and you end up with this. So this is often, this equation right here is often called Newton's version of Kepler's third law. All right. Well, now I want you to do a trick. We're going to do a little trick. We're going to figure out the mass of the sun in the most laborious way possible. We're going to look at the 4 inner planets. And then we're going to draw a graph. So make this, copy down this table. We've got Mercury, Venus, Earth, and Mars, not Mart, Mars. Now, I could go all the way out to Neptune, but those numbers become so big that these little planets, these little rocky planets, just kind of disappear in the data, and we're not going to do that. So here's what we're going to do. You're going to have to do some digging. And this is going to take you a significant amount of time. So I want you to figure out the period. But I want them in seconds. And then I want you to figure out the radius of the orbit of each one of these planets in meters. Now I did this ahead of time, but I don't want to. I'll just let you figure it out. All right. And then I want you to add to this, because here's what we know. We know the period squared. Our prediction is it's equal to 4 pi squared over gm times the radius cubed. So what we want to do is graph the period squared as a function of radius cubed. And so, because look at this, y equals mx plus b. Well, b plus b is just 0. Y is t squared. This should be the slope, and r cubed is going to be our x value. So you're going to need to figure out over here, and this is not going to be easy. I want this is going to be period squared and second squared. And here I want you to do radius cubed in meters cubed. So you're going to look these up. You have to put them in terms of seconds and meters. These have to be in terms of seconds. So then you just take this and square it. And then you'll take this radius and you'll cube it, right? You know how to cube something on your calculator? Raise it to the power of 3. I mean, I'll show you how to do that on your calculator if you get stuck. And then, and these numbers are going to be big. They're going to involve scientific notation, and I'll show you how to massage them so that it looks a little better. And then I want you to graph, make a nice big graph. And you're going to graph period squared as a function of radius cubed. And we'll see if it turns out to be a straight line. Oh, I'm off screen. So here's what I want you to do. I want you to figure these things out. And then I want you to draw a graph for these 4 planets. And I want you to do that right now. So come back to part 3 in just a few minutes.